There are various ways of lifting irregularly shaped items. While the most common lifting devices in robotic arms are flat-surfaced grippers, these types of devices are most efficient with flat-surfaced workpieces and are not nearly as efficient with round, cylindrical, or other irregularly shaped items. When used inappropriately, flat-surfaced grippers can either crush the workpiece or drop a workpiece due to inefficient grip, especially in high-speed operations. A pneumatic mandrel lifting device is used to lift objects that are hollow. The gripping action of a mandrel lift is applied to the interior of the workpiece. Low-pressure air is channeled to a chamber behind a diaphragm. The diaphragm then expands until it is firmly gripping the interior of the workpiece. To free the workpiece, the air is released from the diaphragm, which then deflates, allowing the robot to relinquish the item. Pneumatic pen lifting devices work similarly to mandrel lifting devices. The main difference is the location of the gripping action of the tool. With a pen lifting device, the gripping action occurs on the outside of the part. As the tool surrounds the workpiece, low-pressure compressed air is used to expand the diaphragm. This ensures a snug grip on the exterior of the workpiece. To free the workpiece, the pressurized air is released, which deflates the diaphragm and allows the workpiece to drop freely. The single disadvantage of these pneumatic lifting devices are the limits on the payload or weight which they can lift. However, these flexible pneumatic devices have many advantages, including their light weight, their ability to grip parts without damaging surfaces, and their ability to grip parts with irregular shapes. The first step in the design process for any robot is a risk assessment of its potential hazards. Studies have shown that most injuries occur not during normal operation, but during times when human interaction is most prevalent: programming, testing, inspection, and repair. By system design, robots rarely need human interaction during normal use and operation. But when programming, testing, inspection, or repair is required, humans are more likely to be in the robot's work area or work envelope. Unauthorized access to the robot's work envelope can be hazardous to personnel. Several methods can be used to protect the work envelope. The simplest are known as awareness devices. These devices are only intended to define the work envelope and make personnel aware of the hazards. They do not prevent access and usually consist of small fences or roped-off areas. Guarding methods are used to prevent unauthorized access to the work envelope. The simplest is known as the fixed barrier method, such as a fence or wall. The physical barrier is put around the work area and is configured in such a way that prevents access through, over, or around without a special key or access code. Another method of protecting the robot's work envelope employs the use of presence-sensing devices. These devices detect the entry of a person into a hazardous area and slow or stop the robot. Pressure mats are typically installed just outside the robot's work envelope. When a person steps on the mat, a signal is sent to the robot to stop or slow work. Safety light curtains are another type of presence sensing device. When a person enters the work envelope, the light beam is interrupted, which sends a signal to the robot. For certain work scenarios, sudden stops could cause the work to become uncontained. Objects may continue to move even after the robot stops. In these cases, emergency braking of the robot is used in lieu of completely stopping. With emergency braking, the robot slows down work and does not stop suddenly. Another type of light barrier is called a single-beam photoelectric safety switch. These work in the same way as a light curtain but have only one beam of light, similar to an automatic garage door sensor. Single beams can be useful for preventing unplanned or surprise access to the work area. However, depending on their placement, single beam lights may not stop a determined person from gaining unauthorized access and potentially causing damage to the robot or personnel. The design and location of control panels are also fundamental to a safe robotic design. The control panel should always be located outside of the work envelope but within sight of the robot. Emergency stops should be located in all zones where needed and should be a large part of emergency personnel training. If the proper safety measures are used, robots can be a highly efficient, safe way to accomplish work. Robots come in all different shapes and sizes, but are frequently classed by their degrees of freedom. Each direction of movement on the robot is considered an axis of movement. This robot rotates at the waist, bends forward and back at the shoulder, and moves vertically at the elbow. Each single movement axis is equal to 1 degree of freedom. This particular robot is equal to 6 degrees of freedom. It moves along one axis for each of the waist, shoulder, and elbow joints and along 3 axes at the wrist using pitch, roll, and yaw. These particular motions help to locate the tool in the work area and are called position axes. Most robots have at least 3 position axes to help position the tool in the work area. If the robot were to slide along a track, it would have a 4th position axis of linear movement and another degree of freedom. While the position axes locate the tool in the work area, the orientation axes help orient the tool in relation to the workpiece. The types of movement along orientation axes are defined as pitch, roll, and yaw. These movements all occur from the same joint, the wrist, but along 3 distinct axes. This type of movement is most easily illustrated as it relates to aircraft movement. The robot's tool moves in the same way. Pitch moves the tool vertically. Roll rotates the tool about its center axis. Yaw turns the tool left and right. The position axes movement at the waist, shoulder, and elbow, along with the orientation axes movement of pitch, roll, and yaw, allow the robot to accomplish its tasks within the work envelope.